you had a foretaste of my presentation yesterday during the workshop. So a little bit more theory related to what I talked about yesterday. I changed the title, so I think it's probably more relevant to what I'm going to speak about. So I was asked to talk about the results of the competition that we participated in Pennsylvania. It's called Chambersburg Shootout. A data set is presented to participants in advance for 3 months, 4 months in advance, and you have to predict an unknown set of samples, and then you have to present your results and defend it, and you get questions and you're rated accordingly. This is my colleague Simon. I wasn't there. Simon was presenting on my behalf, and we won this nice little glass trophy, which I don't know who has designed, but it's very nice. Is it designed in Japan?
Yes.
Yeah, okay. It's a very intricate. You have designed it. Brilliant. Very nice. So we use the concept of covariance filters to solve that problem. And surprisingly, the second prize winner also used a similar approach. So there is definitely merit in investigating this sort of approaches in aquaphotomics. Okay. Robustness. So robustness is the curse of NIR spectroscopy. And I come from this company, O'Neill. We deal with off-the-shelf, ready-made calibrations, and we care about robustness. We want to develop solutions that can be used anywhere on any instruments, and we want it to be insensitive to external variations or ambient perturbations. So poor robustness and transferability is always a problem with NIR solutions. And with aquaphotomics, I think it's even more so because it's even more sensitive to temperatures and things that solid samples suffer less from. So I think it's important to deal with this robustness problem. What are those external factors that we need to be resistant against? Type of a spectrometer, optical design, scatter problem. It's one of the major problems with NIR spectroscopy. Temperature variations, humidity, external light, and so on. And things even we don't know that can affect the spectra. Pressure, maybe densities, all sorts of surface physical effects. So one solution, not the only one, but the solution that I think that could address this problem of lack of robustness is to use the repeatability spectra. So same samples measured under different circumstances, which you historically do with aquaphotomics data. Same samples measured different days, different instruments, different temperatures, and use them to downweight the effect of those perturbations or variations. And I'm going to discuss this in more detail. There are many methods, many covariance filters, and some of them might be familiar. I've had a look at the historical work on these methods. As you can see, the year of their inventions or publication, the major papers. Maybe the most famous one is orthogonal signal correction, OSC method, that was developed by Wold. A very popular one is EPO, external parameter orthogonalization, by the French scientist Jean-Michel Roger. The one that I'm going to discuss about is a version of these methods that's called GLSW, generalized least square weighting The main publication is done by Harold Martin. The second prize winner in the competition used this method, REP, which is in the FOSS software. This is one of the methods that you can use routinely. I think many of the NR instruments are FOSS based, so it's worth looking at. It's already inbuilt in their software. Okay, let's look at the geometric interpretation of the concept of covariance filters. So we have a linear model. Just see. Yep. So you have a spectrum and you have a coefficient B, and you project the spectrum onto that coefficient vector, and you get a prediction. So any linear model does that projection, and that is your normalized prediction. Suppose you have some perturbation on your spectral measurement, let's say temperature perturbation or whatever. That can be shown here as delta X. Some amount of perturbation. And that delta X will lead to a delta Y, an error on the actual prediction. So what can we do to reduce that error? Any suggestions? One way is to reduce delta X. So controlled set of experiment. If you can control your experimentation, let's say temperature control, you can reduce that delta X for temperature. So control experimentation is always a solution, but that is not always possible. What else can we do? Pre-processing. All the pre-processing methods that was discussed so far that can address that problem, to reduce that size of perturbation. SMV, for example, derivatization, baseline correction. So you can reduce the error on the prediction by reducing the perturbation there. Another solution to reduce the error is to reduce the B vector, to have a parsimonious model. So the B coefficients could be reduced, not to use too many factors, for example, not to overfit. That can help as well. But there is another solution, and that is to constrain the vector B so that it is orthogonal to that perturbation. So you rotate the B in a way that it becomes orthogonal or 90-degree angle to the direction of perturbation. And this way, no matter what's the size of perturbation, that will be corrected for. So you can approach a zero error with respect to that source of error, if you can come up with that sort of solution. So this is what the covariance filter does, to constrain B in a way that is orthogonal to the subspace of the perturbation. And to determine that subspace of perturbation, we need that repeat measurements. So we need samples, same samples measured under different circumstances, and build the covariance filter or matrix out of that, and use that to orthogonalize the B vector. By the way, covariance matrix have different names in literature. They're called clutter, influence matrix, or interference matrix. You can call them by any of those names. Influence matrix is one of the popular ones. Okay. This is a design of experiments. So you've got samples with different concentrations, but also you have different perturbations, a G2, again different concentrations, a different perturbation, let's say temperature, and same concentration. So it's a very structured DOE. So you can use that to build the influence matrix. How do you do that? Each column is min-centered. So we call it the group centering. Mean-centered and then merged together to create a D matrix or difference matrix or a covariance matrix. And we use that for the to apply the orthogonalization. But we don't have always a controlled set of experimentation. Well, we can have an unstructured design. Let's say sample 1, different concentrations. We have 2 concentrations for sample 1. For sample 2, we have only 1 concentration. But you have for sample concentration 1, you have different perturbations. So you could use your historical experimentation, for example, and merge them all together in a mean-centered matrix called D. And you can use that to downweight your perturbation influence. So to give you another geometrical viewpoint here, if it's your raw data, you have 2 clusters of data, blue and red. If you do min-center on the whole of data on both groups, that's what happens. So you can see the direction from here, this direction changes to this diagonal direction when you mean center. But to create the covariance matrix, we have to mean center each group separately. So we mean center this one, and we mean center that one separately. And what happens is you get the direction where the perturbation is operating on. So this is what we want to downweight. We don't want to downweight this direction, which is related to what we are interested in, identity of the sample or concentration of the sample. We want to downweight what makes the identical samples different. We say why they're different. We want to get rid of that. That direction is undesired. We want to shrink that direction or remove it completely. Some methods try to remove those directions completely. There are hard orthogonalization methods, and some of the methods try to shrink it, like the method that I use. So you will have more control over the level of shrinkage. Okay, this shows you how it works in real life. So you got the first overtone spectra of water. We call it X. Next up, we group center the spectra. Let's say all the sodium chloride spectra that are measured under the same circumstance are mean-centered. All the potassium chlorides are mean-centered. All the water is mean-centered. If you have other studies that you haven't even thought about, you can include them in the same covariance matrix because they could be all relevant. So you end up with a group-centered spectra that is called an interference matrix. Next step, you do a PCA on that covariance matrix, and you end up with PCA loadings. Those are the directions of the interferences that we want to downweight. Those are unwanted directions that we want to orthogonalize or downweight. Next step, an orthogonal projection. So we project the original spectra orthogonally onto the loadings of the perturbation subspace. So it's equivalent of removing dimensions that are irrelevant from our data set. This is that equivalent. And that's what happens. From this, you end up with this. You can see the information comes out of the fairly featureless original spectra. You can see there's not much there, but now clearly see there are different species there, different concentrations. But how many factors from that PCA you want to remove that will affect the final picture? So this is an optimization step that we need to work on. So with GLS, it's very similar to what I just said, except that you have got a gauge. You can control it very precisely. You can fine-tune how much you want to shrink those unwanted direction in the data set. And that factor that is used to downweight, or the level of downweighting, is called alpha. So GLSW shrinks the data space in the direction corresponding to interference signal. And alpha fine-tunes that level of deweighting. So smaller alpha correspond to greater deweighting. A hard orthogonalization like EPO is a special case of GLS weighting. When you completely subtract certain dimensions. You don't shrink it, you just remove it completely. Okay? So let's see how it looks for GLSW. This is when we don't have any deweighting. So alpha is infinite here. It's no deweighting. Those are mean-centered spectra. And you can see the legend here. Red is acetate, blue is lactate, cyan is NaCl, and green is KCl. So let's apply a GLS filter at a low intensity alpha. So alpha 0.01. You can see the information is coming out. You can see that concentration gradient. You can see differentiation between the species. Let's reduce alpha, more deweighting. So reproducibility of the same samples are increasing. You can see that get more overlaid. Those are identical samples that are used to build the influence matrix. More deweighting. So you end up having the risk of removing useful information if you deweight too much. So there's a balance that you need to optimize, where to get there. So this is a very small alpha, a heavy deweighting that could be harmful. Okay, let's overview the challenge results. So the challenge was to identify and quantify. Is that 2 minutes? All right. So identify 4 solutes in water, and we had validation set and data set, and those are the solutes, and concentration range 1 to 100 millimolar, NIT spectra, and we had many replicates, so we could use the same concept of filtering very effectively there. And you can see that we were successful in 100% classification of the unknown data set, which is kind of surprising because some of those concentrations are below detection limit. And it's almost similar to water. We could differentiate those samples from water. So this is a TSKnee plot that represent your original data set into a 2-dimensional subspace. So this is not PCA, but it looks very much like PCA. So you can see how clearly each subset of data are clustered. And those black crosses are the unknown samples. You can see by way of nearest neighbor classification where those black crosses belong. So you could have color-coded boundaries, and you can see where the validations unknown samples fall. And it was very effective. And how we can detect it below limit of detection is something we can discuss. I think you can't do it, but because there were flaws in experimental design, we took advantage of those to be able to do that. So, and this is the quantification very quickly, 1 minute left. So, lactate. So we did an SMV followed by GLSW, an RPLS for variable selection, followed by locally weighted regression, and those are the results of the quantification. Those are the SEP values. They're pretty good, and you can see the number of factors are quite small considering the range. That shows that you can really linearize the system by applying these filters and focus only on the chemical information. And you can see the colors showing the gradients. They very clearly have linearized the response. NaCl and KCl. By the way, you can also see clearly the differences in absorption wavelengths for lactate versus acetate. So each one has a different imprint on water signature. So it really, aquaphotomics is really meaningful here. Water is capturing the information of what is in it. And we historically remove water features from data analysis because we think it's useless, but this clearly shows that water has information in it. NaCl and KCl. Just to give you an indication of what is the detection limit, because we talk about millimolar, 10 millimolar, for example, this is the detection limit. A pinch of salt in 5 bottles of water. So you won't forget that. So that's 10 millimolar, similar to the UV work that was reported by Dr. Mirosawa. Summary, replicate water and water-solute spectra can serve as excellent interference matrices. We have to make use of them. Several influences can be managed simultaneously, not just temperature. You could consider different perturbations at the same time. Corrections are embedded in the model. So the new spectra that come, you don't need to apply the model. Already the space of model is orthogonal to that perturbation. So you can have the raw spectra just predicted by the model. Covariance filters help visualization and interpretation. I advise you to look at the TSKnee. It's a method that is often neglected by Chemometric Society, but I think it gives you more information sometime about the intricate features of a very diverse data set. Best performance is achieved by applying GLSW on raw spectra. So you don't need to pre-process the spectra by derivative methods, for example. We can just apply it on the raw spectra. What we need to do the optimization, and visualization help with that. When you have an optimum solution, when you have a visual, meaningful solution. What next? I suggest that this is a very valuable next step, to use many independent studies data set, which already exist, and combine them to build a universal influence matrix to get rid of many, many different types of perturbation under very different circumstances. Whether that is possible, that is far-fetched, but I think it's worth giving it a go. Thank you very much.
Thanks. We are actually running out of time, so I will go just a very quick question if someone asks. So, Christina.
Thank you for the presentation. In my opinion, it's a very powerful tool for data processing. Just to understand if I'm correct, the advantage of this application is when the perturbation that you have is not constant. Because if I have something that is disturbing my acquisition, but I can keep it constant, maybe only a block scaling can help me. But in this case, the perturbation can be out of control. I'm right?
Yeah, so the main idea is to define the direction of perturbation. And for that, we need to change that perturbation. So it shouldn't be constant. So you have to change that so you can identify the direction of perturbation and then subtract it.
Okay.
So we need to apply that intentionally on the data set.
Thank you.
Yes.
I just want to do a comment to the question, because I think there is no way that we can keep constant temperature, whatever. Yeah. Whatever.
Experimental design in which you have something that was not what you are looking for, and you want to remove the influence of this factor. And I was thinking to apply this approach also to remove some factors that you don't want to take into account.
That's right.
Yeah, the best way is to measure and see the directions, as he pointed out. And now, probably for that, listening to you, I thought we have to have an experimental design, how to measure, and And that now is the question, do we have a way to see the residuals? When you do your orthogonalization, deweighting, we would like to see what are the residuals, because that will be a very important information for the water, right?
Of course.
So thanks, Ali,
Thank
once
you.
again. And we move to the next speaker that is also familiar.